quanta plus 1/2. So even if you freeze the oscillator down to the 0 Kelvin, there is still 0-point fluctuations due to this 1/2. And those 0-point fluctuations can be calculated to have the amplitude of square root of h bar over m omega. And if you take a particular oscillator that we play with, you will see it later in the talk, you come up with the number which is about a femtometer. It's a small number, but it's something that many of you can easily measure if you use well-engineered light. So the dimensionless position of an oscillator can be written as the position normalized to the 0-point fluctuations, and that would give you sort of the motion of the system expressed in the number of quanta of the motion. And the same thing with the momentum. And if we now go to those dimensionless quadratures, then it's nice and pretty, because then those are just canonical variables, and the Heisenberg uncertainty can be written in this simple form, and it stems, of course, from the commutation relation. The position and the momentum cannot be measured simultaneously. And that's, if you will, the origin of the Stern quantum limit. So the bottom line is that good measurement of x, your position, imposes a large uncertainty on p, and the other way around. And this imposed uncertainty is called the quantum backaction of the measurement. So in my first example of the Heisenberg microscope, this uncertain kick that your particle has got from the scattering a photon can be referred to as a quantum backaction of the measurement. And for an oscillator, you can actually write down the position of the oscillator in the lab frame through the position operator and momentum operator in the rotating frame, and they will be the amplitudes for the sine omega t and cosine omega t of the oscillatory motion. So if I want to present you with the kind of pictorial presentation of what happens if you continuously observe your oscillator. So suppose you started your observation at the point where the sine was unity, and then you observe the x. At the same time, according to the quantum mechanics, you impose the back action into p. So quarter a period later, you keep observing, but now you are measuring p because the cosine is 1 and the sine is 0. But you have imposed the back action on the p, and now you're imposing the back action on the x. I'm giving you every quarter period kind of photos, but of course it's a continuous process, and the net result is the more you observe, the more you disturb. And this quantum backaction of measurement will not allow you to make a measurement of the trajectory of your moving object with arbitrary accuracy. And yet, so all that has been the story of a standard quantum mechanics textbook. And what I'm trying to claim here, and I hope you'll join me in understanding that by the end of the talk, is that arbitrary small perturbations in both position and momentum can be measured simultaneously, and the trick is simply to find the correct reference frame. So all this discussion above has been as if you are using absolute values of x and p, but there are no absolute values as such. They all depend on the reference frame. And what I want to do is to use a quantum reference frame, and moreover, a reference frame with the effective negative mass. So let's see how it goes. So one of the possible titles for this story is Trajectories Without Quantum Uncertainties. In the negative mass reference frame, there are certain references you might want to look at for details. So the classical trajectory, of course, doesn't have any uncertainties. The quantum trajectory does. And what we want to achieve is to be able to trace the quantum trajectory without the limitations of quantum mechanics. So Carl Caves and his collaborators used to refer to it as the quantum mechanics free subspaces. And well, I'm not sure I agree with that, because I think this is quantum mechanics in its best. So to observe those noiseless quantum trajectories, we need to make certain efforts. So one of them is, let's define the trajectory relative to a quantum reference frame. This reference system has to have an effective negative mass, and I'll tell you in a minute what it means. And finally, an entangled state of the reference and the probe systems should be generated. So before going any further, let me remind you one of the examples of an entangled state. So this is actually, to the best of my knowledge, the oldest example of entanglement, and it's referred to usually as Einstein-Podolsky-Rosen or EPR entanglement. And this type of entanglement, this kind of state, was first spelled out in 1935 by Einstein, Podolsky, and Rosen, and it was used by them to state that quantum mechanics cannot be a complete theory. So here is how the discussion went. So imagine you have two particles, and according to quantum mechanics, you're allowed to measure the distance between those two particles and the total momentum with arbitrary accuracy, because the difference of the position operators and the sum of the momenta operators, they commute. Because of this minus sign, they commute. Therefore, you are allowed to know this value and this value with arbitrary accuracy. Then their argument would go as follows. Imagine that I am sitting on planet Earth with this particle, and you are sitting God knows where, many light waves, light years away, with that particle. Now, I can make my own free choice, whether I want to measure the position or I want to measure the momentum. I cannot measure both, but I can choose between them. Now, depending on my choice, I will project your system in either the eigenstate of the position or the eigenstate of the momentum, depending on whether I measure x1 or p1. So that would be this instantaneous, as Einstein put it, spooky action at a distance. By making a choice here, you project the quantum state of another system, which is well beyond any signaling cone. And according to them, that was inconceivable. Well, since then, we learned to use with this, to live with this happily ever after. And our picture now is simply that you have this global wave function, which combines those two particles, and there is nothing wrong with this picture, and there is no faster than light signaling. So that's how we live our lives now. Entanglement is part of it. And some 65 years after the paper of Einstein, Podolsky, and Rosen, two groups of researchers formulated the necessary and sufficient condition for the entanglement of two continuous variables. And that would be that you don't have to know the difference between x's and the sum of p's exactly, but you need to know it better than something. And where does this 2 come from? It comes from the fact that I've introduced the variables with the commutation relation equal to I, which means that in the minimal uncertainty state, for two objects which are independent of each other, you can break this variance into variance of x plus variance of x naught plus variance of p plus variance of p naught, and each of them will be equal to 1/2 for the minimal uncertainty state, and then the sum will be 2. So for two systems which are independent and in the minimal uncertainty state, you get a 2. If you get less than 2, you can celebrate and publish in a high impact journal because you have demonstrated entanglement between two systems. So that's the entanglement story. And let's go further. So imagine that I have two objects, one of them defined with a knot. This is my reference object, and the other one without the knot is the object of interest. And I know that I can create a state which is entangled, for which this difference and this sum are well enough defined, perfectly defined actually, for perfect entanglement. And let me put it to 0. So now I'm writing the position of my system as a function of time with respect to my reference frame. Obviously, it's the initial relative position plus the difference between the two derivatives times time. This derivative is equal to p if I take my masses to be 1, this to p naught. And unfortunately, it's not that simple. I don't get the commuting variables here. So this is the difference of x's, this is the difference of p's, they don't commute, and I still have the diverging trajectory because I cannot measure this one and that one simultaneously. But now you already see probably the point that if I take one of those systems to have an effective negative mass, then this minus becomes a plus here because the derivative of the coordinate is minus momentum. And now I have the trajectory, which is defined by two commuting variables, the difference of the positions and the sum of the momenta, which means that if I create an entangled state between those two objects, and I know the difference and the sum exactly, I will know it forever. I can keep measuring, and if my measurement is good enough, then I will just always know the difference between the positions and the sum of the two momenta, which means that I will know the trajectory of my system with respect to the reference frame. So that's the simple argument, maybe even simplistic argument, but this is the backbone of the rest of the story. Obviously, the same can be discussed for an oscillator, and for an oscillator, in fact, the negative mass is equivalent to the negative frequency and the negative elasticity, because in this case, again, the minus is turned into a plus. And it is possible to demonstrate that up to certain conditions, there is an equivalence between the entanglement and the ability to observe the motion of my oscillator with respect to the reference oscillator with arbitrary accuracy. Okay, so let's go to physics now. Let's discuss oscillators that we will be playing with in this talk. So one of them is the spin oscillator, and the other one is the mechanical oscillator, and the third one is the light oscillator. For the spin oscillator, the non-commuting variables corresponding to x and p will be actually the projections of the spin on the direction orthogonal to the macroscopic oscillator, to the macroscopic orientation of the spin. For the mechanical oscillator, this is obviously just the cosine and sine component of the oscillation. And for light, as I'm sure many of you know, the x and p quadratures correspond to the quantum mechanical amplitudes of the sine and cosine component of light. Okay, so let me introduce the mechanical oscillator that we're playing with. What are the requirements for a mechanical oscillator that would be good enough for us? The requirements are that it has as high mechanical quality factor as possible. And that is because otherwise this oscillator will be coupling to the surroundings and its quantum state will not live for too long, because the quality factor of the oscillator defines how fast this oscillator exchanges energy with the external environment. And since it is not feasible to run this experiment so that we can cool this oscillator down to its ground state by simply cryogenic means, therefore we need a very high Q. So the certain numbers for those oscillators are given here. Just very briefly, what you are seeing is essentially a membrane made of silicon nitride, and there is rather elaborate phononic band gap structure, which prevents this oscillator, which is the central part, from exchanging energy with the environment, which is beyond the frame of this membrane. The membrane has a thickness of about 100 nanometers, and the size of it is millimeters. So it's really a macroscopic object. You can look at it. It's very thin, but still, it's a macroscopic oscillator. So we are able to make those oscillators with the Q factors as high as 1 billion, and they oscillate at the frequency of about 1 megahertz, mechanical frequency. And if you take all those numbers together, then you will see that indeed the 0-point fluctuations are of the order of a femtometer, and at 300 Kelvin, you have about 1 million phonons there, so you have the oscillations of 10 to minus 12 meter. How do you couple light to such a system? Well, you take this membrane, which oscillates like that, and you place it in an optical resonator. When you shine light into the resonator, you have a standing wave. You place this membrane not in the node and not in the antinode, but somewhere in between. And then you have a piece of dielectric which oscillates. And this oscillating piece of dielectric generates side bands on the light corresponding to the oscillation frequency. So now, depending on how I tune the input frequency, this frequency, with respect to the resonance of this resonator, I can choose whether I make the lower sideband of this light happy or the upper sideband. Happy meaning that, for instance, if I tune my input laser above the frequency of the resonance of this optical cavity, then obviously the lower sideband will be on resonance with the cavity, it will be enhanced, and therefore scattering of light from the laser into the lower sideband would be preferred. So in the Hamiltonian of interaction, that means that I am scattering light and creating a single photon of the lower sideband, that one. Since the energy of this photon is lower than the energy of its father photon or mother photon, that means that I need to create a phonon in this process just to conserve energy. So this is the interaction of the kind A dagger, B dagger. And for those of you who work in quantum optics, this is a very familiar Hamiltonian. It's an entangling Hamiltonian. It creates a pair of excitations which are quantum correlated, a photon and a phonon. By simple tuning the input laser on the other side of this resonance, I can now favor the upper sideband, the blue sideband. And this blue sideband has a higher energy than the original laser, and therefore this energy should come from taking away the single excitation from the membrane. So you can think of it as a beam splitter interaction, or you can also think of it as cooling, because I shine light on this system and I take away phonons from it. So this is the mechanism of optomechanical laser cooling of mechanical motion. So I can have this interaction or that interaction, and if I tune it sort of in the middle, then I can have both interactions. And for quantum mechanics, for quantum opticians in the audience, you probably know that if I add this and that, then I would get something which is called a quantum non-demolition Hamiltonian, which means that if I measure the X quadrature of light, I am not disturbing the mechanical X quadrature, but I can actually measure the P quadrature of light and so on. Okay, so now we take this mechanical system, we put it into the, where is my cursor? Into an optical resonator. The mechanical oscillator oscillates. In my case, it oscillates at the frequency of about 1.3 megahertz. The engineering of this phononic band gap allows me to have a very clean spectrum within the phononic band gap range. And it's engineered in such a way that the mechanical frequency is exactly in the middle of this phononic band gap structure. So that simply means that A, I don't couple to the external noise, acoustic external noise, and B, my Q factor can be really, really high. So when I now shine light on this system, I shine it continuously and I keep measuring. And as I told you in the beginning, if I keep measuring an oscillator, if I do it right, the quantum mechanical back action will actually dominate the measurement precision or imprecision. So instead of measuring the motion, I would actually make this motion more uncertain and more chaotic. It's like as if I'm heating it up with the quantum fluctuations of light. The mechanism for it can be attributed to the radiation pressure. You can think of it as photons bombarding this membrane and causing it to move as if it has a higher temperature. So in this graph, you can see that this hardly visible resonance is corresponding to the actual motion of the membrane at the temperature that it acquired. And the whole thing here is due to the quantum backaction. So I'm in a very good position here because my motion is now dominated by the quantum backaction. And if I manage to somehow eliminate this quantum backaction by choosing the correct reference frame, then I should be able to make a good observation of the motion of this membrane. Well, for the experimentalists, this is actually the bits and pieces. We work by placing this resonator, optical resonator with the mechanical membrane inside in this relatively modest cryogenic system, 8 Kelvin. For people who are doing serious cryogenics, this is almost as room temperature. But for us, it's very important that we have good optical access. As you can see, those nice and large windows allow us to shine light there, to get it out there without losing quantum states. This is very important. And inside, we have our membranes with the phononic bandgap structure. All right, so now let's get to our negative mass oscillator. And this is atomic physics. So let me assume that I have a two-level system, an atomic two-level system. Let's say it's a ground state of my atoms, and let's say I put it in the magnetic field, and so I have spin up and spin down possible orientations. Now I want a large atomic ensemble. Let's say I have many, many atoms, and by optical means, I can orient them all so that they are all spin up. So this is now my macroscopic projection of the spin, Jz. It's macroscopic, and therefore I can take away the operator on top of it. And so the two interesting projections of this macroscopic spin are the projections on X and Y axis. And according to quantum mechanics, if I have this kind of commutator, the minimal uncertainty of the direction of this macroscopic spin will be something like the square root of the number of atoms times 1/2. So if this is, let's say, 10 to the 12 atoms, then this will be something like 10 to the 6, and the angular uncertainty will be something like 10 to -6. So it's a small uncertainty, but it's the quantum uncertainty we deal with. Now, how do we make an oscillator out of it? Well, we put it in the magnetic field. And we put it in the magnetic field, and the whole story begins to oscillate around the z-axis. Obviously, if it would be a classical system, then oscillating around z-axis will mean nothing. But in the quantum world, what is oscillating is actually quantum projections of this microscopic spin on the orthogonal axis. So the donut that I'm showing you here illustrates the state where I scattered one atom in such a way that it's flipped. So I scatter it in such a way that I don't know which of the spins has flipped. And that means that I have this coherent superposition. And in quantum mechanical world, that essentially means that I have created the first excited state of this oscillator. Now, I call this an oscillator with the effective negative mass. And what right do I have to do so? Well, imagine I have this Bloch sphere, and its ground state corresponding to the minimal uncertainty state is all spins up. And now I am creating a state which corresponds to this first excited state. In fact, let me create any state from this ground state. It will always have the size which is greater than the ground state. But if you think of a sphere and you create a state which is slightly bigger than the minimal uncertainty state, this state will be a little closer to the South Pole because of the curvature. So that means that by creating an excited state of this oscillator, I'm reducing its energy. And this is the negative mass oscillator that I'm talking about. And it is embodied in an atomic ensemble in magnetic field. In the experiment, you can work with different kind of atoms. We are working with room temperature atoms, believe it or not. And the reason we can do that is that we place those room temperature atoms in very special environment. So you see here a little glass vessel with the little channel inside. And we have cesium atoms, which are freely moving around inside this channel. And typically, if atoms move around inside this channel like that, then every collision with the wall will randomize the spin and will kill the quantum state, and that's no fun. But luckily, there are coatings that one can apply to the walls of this cell, and those coatings allow the spin state to be preserved over 10 to the 5, 10 to the 6 collisions. So you have a system which may be an oscillator if you put a magnetic field on it, and it can maintain its quantum state for 10 to the 5, 10 to the 6 collisions, which essentially, with room temperature atoms and the size of this channel of about 1 millimeter, can be converted into milliseconds of coherence time. So you can have a system containing lots of atoms, which can be an oscillator with high Q. And the point is that by optical pumping, you can initiate this spin state in its ground state of the spin oscillations, and depending on the direction of the spin with respect to the magnetic field, you can initiate it in the either negative mass state or positive mass state, as you will. And it's as simple as that. You just simply change the direction of the magnetic field with respect to the optical pumping direction. Okay, so measurement of this spin state. You have linearly polarized light. It has, of course, its quantum fluctuations corresponding to the shot noise. We have your atomic spin, and this spin is not directed exactly along the vertical axis because it has inevitable quantum fluctuations. Certainly they are exaggerated here. The real scale is more like this angle is about 10 to the minus 6, sorry. but that's what's happening. So you shine light and you make a measurement of the polarization rotation. If the projection of the spin on the direction of propagation oscillates according to this Zeeman oscillations, then obviously the polarization will also oscillate, as we all know, and we will get an oscillating signal in the photocurrent. It will oscillate at the Zeeman frequency, which can be tuned with the magnetic field. And long and behold, you will be simply with the locking amplifier being able to measure the cosine and the sine components of those oscillations, which will correspond to the cosine and sine components of those oscillations, which will correspond to the measurement of the projections of the spin in the rotating frame. And if you recall the beginning of the talk, then in fact, one of those projections can be associated with the x quantum variable and the other with the p. But look, I am measuring here continuously. Therefore, again, as with the mechanical oscillator, at a certain time, I'm measuring, let's say, the one projection and imposing back action on the orthogonal one. And a quarter a period later, I'm measuring the other projection. And again, the more I measure, the higher is my quantum back action. And this is a very similar drawing, a very similar graph to the mechanics, where again, I'm demonstrating you that with our system, we can be quantum back action limited. So for people who are experts in atomic physics, I can tell you that the origin of this back action is simply the quantum fluctuations of the Stark shift of my atomic levels brought about by shot noise of the probe light. So I shine probe light on this system. This probe light has its quantum fluctuations, shot noise. This shot noise converts into the noise of the Stark shift, and this converts into the fluctuations of the spin state, and that's what we observe. Okay? So now I've introduced you to two systems. One is the mechanical oscillator, and the other one is the spin oscillator with the effective negative mass. And now I can implement the story that I told you in the beginning. Theoretically, that if I combine the measurement on those two systems, then I can hope to reduce the quantum back action and to make a measurement beyond the Stern quantum limit. That's the piece of the experimental setup where our atomic system is sitting inside the magnetic shield, light goes through, and so on. So this is the system that we will be looking at now. We take light, we shine it through the atomic spin ensemble, then through the cavity containing our mechanical oscillator, and make a measurement. That's the atomic system, that's the mechanical system. And the result of this experiment was published a couple of years ago. And that's the reference. So we have our oscillator, mechanical oscillator, we have our spin oscillator in the negative mass regime. And this is what we observe. Before going to the observation, I actually wanted you just to give a glimpse of how we can actually match the strength of the measurement on the two systems. And I don't want to go into too many details, but just giving you a gist of it. The interaction constant in optomechanics is actually basically just given by the number of photons in the strong field. So this is theoretically very easy. The stronger is my laser, the stronger is my measurement, and the higher is the quantum back action. With atoms, the corresponding figure of merit is the optical depth. This is not only true for our experiments. For many experiments dealing with the free space atomic ensembles, quantum cooperativity simply converts into the resonant optical depth of the ensemble. So we need to play with those two systems to make effectively high optical depth and to build a high Q mechanical system and shine a lot of light on it. And the result is the following. So if I first measure on the membrane, and I've shown you already this result, this is more quantitative. So make a measurement on the membrane, and the checkered area is the quantum back action, and it dominates over all other kinds of noise. And if I now work on the atoms separately, I also have the result of the noise dominated by the quantum back action. And now I move my atoms simply by changing the Zeeman frequency in resonance with the mechanics. And if things wouldn't be well engineered, then the total back action will be just the sum of this area and this area, but in reality, it's actually the difference. And this is what you see here, that this is the logarithmic scale, by the way, notice. So by adding the two systems, I have the destructive interference of the quantum back action. And the result is that I have 6 decibel, a factor of 4 reduction of the quantum back action because of this destructive interference of back actions, because of the negative mass reference frame of my magnetic oscillator. So this was the first step that we did 2 years ago to show that we do indeed have the destructive interference of quantum back actions, which means that we're in a good position to try to create an entangled state of those two very disparate, distant, macroscopic objects, an atomic ensemble and the mechanical oscillator. So those are the heroes in the lab. And to generate the entangled state, I need to generate a state which would have the variance of the difference of x's and the variance of the sums of p's, well, not exactly going to 0, but at least corresponding to the entangled state. I have, maybe 10 minutes left. Is that the accurate statement?
That's about right, yes.
Okay. So let me give you a qualitative picture of how you can see or visualize this entangled state. So this is the phase space for a mechanical oscillator, the P and X phase space. This would be the ground state of the oscillator, and this large uncertainty is its initial state, which can be even thermal. So what happens is the following. as I have random exchange of phonons with the environment, my state jumps around. But if I have a reasonably long coherence time, and with my Q factor of 10 to the 9, I do have a reasonably long coherence time, then I can think of the system as just frozen somewhere for a fraction of a millisecond. Now, my magnetic oscillator, as I told you, it's actually a very nice ground state oscillator, and it has a reasonable coherence time. So for a fraction of a millisecond, even close to a millisecond, I can have those two states kind of frozen with the corresponding uncertainty. And if I measure on those two, I have the uncertainty which is dominated by the quantum backaction. So this is the quantum backaction that I've shown you for the mechanical oscillator. This is the quantum backaction that I've shown you for the magnetic oscillator. An entangled state would mean that within those two uncertainties, the states can be anywhere, but they're always such that they are completely correlated. So they can jump, but they're always correlated. So this is sort of the visualization of the entangled state in the continuous variable frame. Each of the two states is thermal, taken separately, but they are quantum correlated in this sense. So I don't think I have much time to explain how we actually do the measurements and confirm the entanglement. We use the signal processing machinery called Wiener filtering. I don't think I have time for that. But trust me that we're measuring on those two oscillators. And as a result of this measurement, we get the photocurrent, of course. And we process this photocurrent in such a way that at every instant of time, we can predict the state of the composite system. We can predict the difference of x's and the sum of p's. And we can predict it because we're measuring commuting variables. And then we compare this prediction with what we actually measure at this point. And we do it continuously. And if our prediction corresponds to what we actually measure, to better than the uncertainty, the standard quantum limit, then we claim entanglement. This is actually what I show you is the trajectory as promised from the beginning. And it's the predicting trajectory and the actual trajectory. And as you will see here, hopefully, the two curves are following each other very closely within the ground uncertainty of the states. So that essentially means that I can predict the trajectory of my system to better than the standard quantum limit of the uncertainty, and that amounts to entanglement. So this is the result of the entanglement. Unity for the total uncertainty of x1 minus x2 and p1 plus p2 for the two systems corresponds to the boundary between non-entangled and entangled state. We're below that. It's not infinitely below, it's 20% below, but you know, it's not much, but it's home. We're improving on that. All right, so let me spend my last 5 to 6 minutes on telling you what does all that have to do with the gravitational wave observation. And as you all know, one Nobel Prize has already been awarded but nobody says it's going to be the last one, so it still makes sense to work on the subject. So a few years ago, they observed gravitational waves. How did they do it? In very pictorial way, they have an interferometer. This interferometer is just this Michelson with the length of the leg of 4 kilometers. In the end of each of those tunnels, there is a suspended mirror here and here. And the gravitational wave is a quadrupole wave. So it actually shrinks the space in such a way that when it goes this way, it goes that way, and the other way around, when it goes this way, it goes that way. So it unbalances the interferometer. You want to measure this unbalance as good as it gets. They shine quite a lot of light into here. They actually shine many watts, and what they get is many kilowatts of oscillating light power. And those kilowatts, they bombard those kilogram mirrors with a lot of radiation pressure. And so, not surprisingly, they are in the regime where they are quantum backaction limited. And here we go. If this is a situation where they are quantum backaction limited, maybe we can help them. So that's what I just told you. This is what they observe now. This is the minimal displacement of the mirrors that they can observe as a function of frequency. The gravitational waves are centered around few hundred hertz, so from few tenths of hertz to a kilohertz. And when they are looking at high frequency components, this corresponds to short observation time. And for short observation time, they are limited by short noise of light. And for lower frequencies, they are limited by the radiation pressure because it's longer observation times. And in between, they have exactly this standard quantum limit or very close to it. And now, can we actually drive this whole curve down? It's the repetition of what I already told you before. All our experiments so far are done with tiny mechanical objects which are oscillating at high frequencies. Now, this is the experiment where you have many kilograms oscillating at very low frequencies, but still the principle is the same. So in a very naive way, we just want to put our atomic oscillator with a negative mass somewhere in the vicinity of this big thing and see if we can cancel the quantum backaction. Definitely nobody is willing to admit us to this machine before we show some proof of principle. So we're trying to show the proof of principle in the lab. That's, the same story of the negative mass. And we have put forward a couple of theoretical proposals. One complication is actually that so far all the experiments were done with the same laser pulse that propagates through the atoms and through the mechanics, which was tuned obviously to the atomic frequency because the mechanics doesn't care. Well, the mechanics doesn't care to the wavelength of light if it's not the mechanics of the gravitational wave interferometer. There they use 106 laser and they are not willing to negotiate. So instead of using one and the same beam of light going through the two systems, we have to use two entangled beams of light. And that definitely sounds familiar, at least to the quantum optics part of the institute. So we need to generate an entanglement between the light that we shine on the atoms and the light that will go into the gravitational wave detector. Because then the quantum fluctuations of those two beams of light will be entangled, and it will be as if we're measuring with one beam of light on the two systems. And then we will take the signal from this detector, combine it with the gravitational wave interferometer signal, and hopefully suppress the back action of measurement. So this is just to show you that indeed, if I have a measurement on my atoms and a measurement on my interferometer, there will be the parts which are due to the back action of light, and it will contain the x quadratures of the two entangled beams. And there will be the parts corresponding to the shot noise, which will contain the p quadratures of the beam. And if the effective mass of one system has an opposite sign to the other one, then when I combine those two, I will get what I want to get. And that is, I should be able to suppress the back action in the broad range of frequencies. And according to our, we hope, realistic estimates, we should be able to improve the signal to noise ratio of gravitational wave detection by several decibel. So we're building the entangled light source. We have already observed about 8 decibel entanglement between those two colors, which is a record in its own right. Those heroes are putting together now the entangled light source and combining it with the atomic noise eater. And as you all know, there is the Einstein telescope, the European response to LIGO, to the gravitational wave detector in the drawings. So I'm sure we will demonstrate the principle before this thing is built, but we'll see what happens. So this is the bottom line. If you do things right, there is no quantum limits for the precision of measurement of motion, force, and gravity. The next generation of sensors on the way. And I thank you for your attention.
Thank you very much for this very fascinating presentation. I'm applauding on behalf of the entire institute.
Thank you.
It's actually fascinating to see that something that I at least don't get to work with everyday quantum mechanics, how far this can actually be pushed and how clever this can be used for not just some academic demonstrations of effects, but to help solve making the most important or the most interesting measurements at this day and age even better. I'm sure there are questions. So I don't see any questions so far, which gives me the time to ask.
Can I ask you a question?
Yeah, of course, sure.
Hi, Eugene. Thanks very much. This is really very encouraging and very inspiring. Can I ask you some questions about little details of the experiment? So how you emphasize that you want to have large windows to collect a lot of light. Can you say something about the efficiency with which you have to couple your mechanical oscillator and your atoms, and how kind of, let's say, fragile your results are in that term?
Right. Thank you for the question. So essentially, this is continuous variable entanglement. And everybody knows that if you have 10% losses, then the best you can get is 10 dB of entanglement. If you have 10% losses in each channel, then it's as best, 80% of entanglement and so on. So losses are the name of the game here. And it goes simply from minimizing all kinds of anti-reflection coating losses and so on. And of course, the most interesting part is what can we do about losses in the mechanical system, as you just mentioned, and the spin system itself. So for the mechanical system, essentially, if I go here, so we simply need to have a very, very, very single-sided cavity. So we have at the moment the cavity with something like 1 to 20 relation between the output coupling and the intracavity losses. The intracavity losses, we paid a lot of money for coatings, and so the coating losses are minimal. And thankfully, the membrane itself, made of silicon nitride, is actually a wonderful thing. And with 100 nanometers thick membrane, we have not been able to measure absorption losses on it. So it's definitely below 10 to minus 6. So in this sense, life is good. There are, of course, many other problems like, tiny misalignment of this membrane will kill the whole thing. With atoms.
Sorry, so about the membrane, your membrane is this phononic crystal thing. And so how much scattering do you get because of the texture of the membrane?
So the point that I probably not emphasized strongly enough is that light is here. Light is only in the central part of it.
Okay, and that's how large? That's about a few microns.
No. This is like, this is 500 microns.
Oh, okay.
This is a 100 micron thing.
I see. Okay.
So this whole business is just for the phononic insulation.
Got it.
Of course, this membrane itself has its own mechanical modes, which are a nuisance. They are typically at tens of kilohertz or 100 kilohertz. So this has to be stabilized so that it doesn't bounce back and forth. But this is also possible. And then this little drum is oscillating at 1.4 megahertz.
Okay. Pascal had also a question related to the membrane, so maybe we should have his question next. Do you want to unmute yourself?
Yes. Thank you very much for the very beautiful talk.
Thank you.
Yeah, my question is whether you can somehow increase the mechanical frequency of these membranes to be naturally closer to the ground state. I don't know whether could you tension the membrane, for example, or could you reduce the size or change the shape, or is this some sort of sweet spot?
Sorry, so the question is, can I tune the frequency?
No, sorry, whether you can increase the mechanical Q factor of these membranes.
Well, for this kind of devices, this is as good as it gets worldwide. And I have to give a lot of credit to my graduate student, Yagish Tsaturyan, who is now at the University of Chicago, and my colleague, Albert Schlisser, here at the Institute. And I started all this optomechanics business some 12 years ago or something, because I thought, oh, damn, this sounds simple. And so we purchased just silicon nitride membranes from Narcada company that uses it for Windows. And that was with the mechanical Q of 10 to the 6. And then we started working on the phononic shields and improved it to 10 to the 7, to 10 to the 8, and now to 10 to the 9. So for those membranes, this is as good as it gets. There are other systems which are smaller. For example, Oscar Painter works with his one-dimensional systems, which have the product of the frequency. So our product of frequency and Q is something like 10 to 15. 10 to 16. Oscar has it a couple of orders of magnitude higher, which is also important because the eigenfrequencies are 6 gigahertz there. So at 6 gigahertz, if you just put it in a Dilfridge, you're in the ground state, no problem. So for other systems, the answer to your question is yes, you can have it with a higher Q, and you can have it close to the ground state, even at Dilfridge. However, for us, it's very important to have those low losses. And also, in the end of the day, we would very much like to go to lower frequencies rather than to higher frequencies.
Okay, thank you very much.
Okay, we have 2 more questions by 2 Maria. So maybe Masha Chekova first.
Oh, thank you. First of all, thank you, Eugene, for a really beautiful talk.
Thank you, Maria.
But I have a question about the last part, the gravitational waves. Normally, normally
I can't hear it, sorry.
also other
you're
work with radio squeezed vacuum, right? And your proposal assumes that there is also entangled light entangled with some other.
I think
Really?
I guessed the question. Let me repeat the question, Maria, because the connection was weak. But let me repeat the connection, and you just...
Maybe you can read my...
Yeah, so I mean, you probably guessed it, but what she was asking whether, so at present in the LIGO detectors, they use squeezed vacuum.
Right.
The question is whether that should be replaced, your approach should replace that, or if that can be combined.
It's a good question. So at present, squeezed light is used. And you can have either squeezing in one quadrature or the other. So if this curve, or rather, let me show you some experimental curve. Right. So right now they are somewhere here. And if they use light which is squeezed in the phase quadrature, they will reduce the noise here and improve the sensitivity at the cost, of course, of increasing the uncertainty in the amplitude quadrature, raising this. So using squeezing with the fixed phase simply amounts to moving this curve left and right. You cannot improve the sensitivity over the entire band. Admittedly, there are also proposals which suggest to use external cavities to rotate the phase of squeezing so that it rotates from phase squeezing to amplitude squeezing over the range of a few hundred hertz. This requires building 100-meter long filter cavities, and if they want to do it, I cannot stop them, but I would argue that our approach is at least kind of more compact, and I personally like it much better than just building cavities, forgive me. So, I mean, it remains to be seen whether this is going to be competitive and whether this is going to be the thing that will be implemented first. But so far, with all honesty, there are several competing proposals for the broadband quantum noise reduction, and this is one of them.
Very good. Then I would take one final question by Maria Romodina, and maybe...
Yeah. If we take a look on trajectories of your system, we saw two trajectories. One is measured, and second one is prediction.
Mhm.
And it looks really very random. This trajectory is like a,
Mhm.
and that's why I'm asking how long you can predict the behavior of your system. How long the time?
So the randomness of those trajectories is simply because you have random quantum and thermal fluctuations, and you have random quantum backaction. The quantum backaction is suppressed for both systems, but it's certainly not suppressed for each system taken separately. Remember, I've shown you this picture, right? So if I now take the slideshow from here, right? So this whole thing is just kind of moving around like crazy. And it's this motion of the red dot that you're looking at when you're looking at the whole thing. But when you're looking at the correlations between what you predict and what you observe, then, as I've shown you here, they are following each other very closely, right? Right?
Yes. So as I understand, you use a measurement from the first system to predict the behavior second?
No.
This is
it's a measurement on both. So how do you demonstrate entanglement? You make a measurement, you wait, and you make another measurement.
I see.
And if there is no decoherence, and if your measurements are good enough to generate entanglement and preserve it, then you should have the results of the two measurements, both for x1 and x2 and p1 plus p2, the same. What is shown here actually is a combination of the difference of x's and the sum of p's, because the x's are here and the p's are here, right? So it's a two-dimensional plot.
Okay, thank you.
Sure.
All right, we should probably cut this off. We're already at an advanced time, but thank you very much for this recent insight into your current activities. It's a really fascinating topic. Thank you very much for the honor of giving this DLS seminar to us.
Thank you very much for inviting me, for your questions, and for giving me the opportunity to step out of my office.
If at least virtual, right? So we still have some individual meetings following up, and you should have gotten a separate Zoom link.
Yes, I did. Mm-hmm. So thank you very much, and goodbye to everybody. Hope to see you live some point in the near future.
Yeah. Thank you.
Thank you. Bye.